Hopefully, I've changed the camera view, Prim, so you can relax now. Yeah. So they can only get to see me at the moment. Yeah. Thanks, everyone. There's Simon Holbeach. Hopefully, everyone knows me. Help run Bath Astronomers. Welcome to our June session. And we have a special guest with us, Dr. Megan Argo. And she's going to give us a little talk entitled The Next Blink of a Cosmic Eye, Astronomy in the Next 200 Years. I think she first gave the talk in 2020. So lots of things have potentially changed in the last 2 years in terms of insights, in terms of problems, in terms of opportunities. So if you did see it then, you'll probably get a bit of a refresh or new insights as well. So should hopefully be loads of questions at the end. Please ask lots of questions. Okay. Oh, it's going to work. Okay, so let's move it. Oh, click on the screen. So the clicker actually works. Way. Okay, so James Webb Space Telescope, the first science images, the color images are going to come 12th of July. So stop everything, don't go to work. 12th of July is just watch the internet and watch the first images and go, wow. Okay, they had a press conference today, which was full of Americans going, it's going to be amazing. So if I dial them down halfway to more of a British, it's amazing, it still sounds like it's going to be very amazing what they're going to show. So I'm very much looking forward to that. There's 6 people who help look after the group. So we've got Camilla, Chris, Jonathan, Mike, Prim, and myself. Photos there, just so you can stop them in the street and ask a question. They're hopefully approachable, and some of them even live quite close to Bath. There's 81 of us all in total. Numbers have dipped, just a couple of joint memberships have lapsed in the last month or so. I'm going to encourage them to rejoin, so we'll get back up to 85 where we were, fingers crossed. But that's a reasonably good and healthy number. So at the moment, at the last meeting for this effective year, we run from September through to June. We're in a reasonably healthy position for our club, so great. And now my gadget. Oh, I have to be here. Right, so what have we been up to in the last month? We went to a lovely little, this is Corston, they had a fair last year, and they're not running it this year, but they've actually just rented out a whole area, which they've turned into a community orchard, and they launched the community orchard. So they invited all the families from Corston Village to come along and just have a picnic and listen to a band. And we got invited along as well. But as you can probably see from this solar scope, just in the middle here, which is covered in a plastic bag, it wasn't the best weather for solar, but the kids were looking at Australia using the DOB there. And you can see this keen chap here on the pump with the grey t-shirt and the red white motif on it. He spent most of the time sort of pumping up and launching rockets for everyone. So it was a sort of a fun activity, even if the sun didn't show its face. They did have a beer tent, and everyone was very, very happy. We also did an event, solar outreach, in front of the Royal Crescent, just at the end of May, just after our last meeting. And we found some wonderful characters all dressed up in a period costume. So they also had a look at the sun through the Coronado and through the various other scopes. So thank you very much for the posing. And thank you for Jonathan. I don't think he's with us at the moment, but for the photos and the shares that we got. So that's great. It's a really fun day, but we weren't just there for the solar. We actually did some sections for the Sky at Night program. So that's me looking very, hey, that's me looking famous. That's, we'll see what it comes out. It's going to be out on the 11th of July. So we'll find out. But that was covering what our outreach activity and my views on outreach. So let's hope not too much is cut out of my views on outreach. We also attended this. Can you guess what it is? It is. There's a bat just went past. And you can see them all going around the trees. So this was the Festival of Nature, and we took part. So we did the back walk first, and then once the back walk finished, I did the night sky. So I came on after this guy. And unfortunately, he's amazing. He's a really, really good. He knows his stuff. He's the local bat guy for Baines. And following on from him was quite difficult because not only did he do a good show, but they'd arranged it so early, we had 2 stars. Now, it's quite difficult to do a stargazing evening with 2 stars. I was complimented on how I managed it. I'm not sure whether that's when you're telling little Junior that despite the terrible mess of a picture in front of him, that's really good. I don't know, but he did a really good job. And actually, I'm thinking that potentially things like having a bat detector and things for some of our observing nights, unless you're scared of bats, might actually be sort of as the early part of the evening might be an interesting sort of addition to it. Maybe for school groups and things like that, more on the outreach side. Then you look like you're absolutely petrified of bats. Okay, perhaps we won't do it when you're there. What else did we do? We did the summer solstice stay, and for a Tuesday, this is at the Herschel Museum, so it's where we are tonight. We had over 80 guests come in, which is absolutely unknown for a Tuesday in the museum. So it's really good for their books, but it's also good for their Herschel 200 season for commemorating the 200th anniversary since the passing of William Herschel. So we had loads of people coming in through the door. We had school groups coming in. We had people from the old age, sort of St. John's Foundation for the sheltered housing. They came in as well. And we had 2 or 3 people guiding on telescopes. It was absolutely chaotically wonderful. It worked out really well. We were just talking all day. We really didn't stop. So that was a very fruitful, rewarding day for everyone. And all the kit got used. That's great. We went out again. This time, this is just weekend just gone. We were at Bath Eastern, and we had the fancy dress out. We had the solar scopes out, stomp launchers, the compressed air launcher. What else did we have? We had telescopes, solar scopes. We had loads of stuff. So the kids had loads of fun dressing up. And it's a tough time when you're an astronaut. Now you have to launch your own rockets. But the kids seem to like that. And here we've got Tony helping this young lady dressed as an astronaut. Started the countdown there. I'm going to have to make a simpler one of these launching mechanisms. It's counting down. Woof! And off it goes. Yeah, and there's a wishing well just over there, and it actually landed. The rocket landed in the wishing well. So we were dive bombing people with rockets all over the place. From a health and safety perspective, you'd think the organisers would hate us, but they loved us, and we get invites back to all the ones we do. So big thank you to Merrick for coming along, and for Tony for helping out. It was absolutely great. At one point, and this is one of the ones, there were so many people inside our gazebo, we couldn't go into it. Okay, there's so many parents and kids in there making rockets and sort of getting stickers and doing all that kind of stuff. We couldn't get in there. So it's good, but it does mean that we lost. We've got models of the solar system, and our moon disappeared. So we have no moon anymore, but we can probably cobble one together. And it's delightful that over 100 people enjoyed themselves, and someone's got a trophy for their bedroom wall, but we'll just have to see. And even mums who are sort of where they're abandoned by dad to go off to the bar, they're having a good time as well. So we've got some observing going on there. I think they're looking at some of the houses nearby. But this is it. This is our last talk of this season. So the 2021-2022 season is gone. Right. So we won't be all dull and sort of all bored, but there are things to look forward to. And here is this wonderful piece of, now I'm going to call it wonderful because you complimented it. Yeah, so on the 7th of August, we're taking over this shop in the centre of Bath. It's a regular thing that the BID team do to try and encourage charities to get more exposure, but we've been invited in alongside the Herschel Museum, Herschel Society as well. So we'll have telescopes outside, we'll have telescopes inside, loads of activities for kids as well. So on Sunday the 7th, we'll be doing that. Looking forward to that. So if anyone wants to come along, please feel free. Not only just to participate, bring your family and things like that, but encourage other people to come along. So it should be quite good. And we've got other things going on. The planetarium that we've stolen from University of Bath. If I could write the shows for it, because it looks like I am doing that now. We've got shows on the 8th of August and the 22nd of August. And then we've got 3 more fairs that we're booked in for on the 3rd, the 10th, and the 11th. So that's just the outreach side of stuff. Just actually got a request in for the 4th as well. It's September to start off with is going to be quite busy on outreach and fairs and things. But it's one of those ones where you get, the more volunteers you get, the more rewarding it is for everyone, because sort of you get more time with people coming around. The kids get more time with someone who's talking to them about their interest. And we even had people bringing their own telescopes. They came to the fair, saw we were there, and they came back with their telescopes to say, it's broken, what do we do with it? Thanks, Merrick, for saying. Someone came to talk to Merrick, we've got a broken telescope. Oh, bring it along. So yeah, that's exactly what happened. But there are other serious things going on. We've got at the moment, although it was advertised sort of in a big way of, oh, you've got to go and see it last week. The planets are still lined up in the morning sky. Mercury's getting a little harder to see, but it's still technically there. And if you can't see Mercury, there's still 4 planets to actually have a good gawp at. And if you've got a telescope, you can get Uranus as well within that field. Neptune maybe a little too hard. We've got the solar outreach, so Sky at Night program on the 11th. So we'll hopefully get a little bit of coverage in there. So that might actually, maybe it'll drive a bit of membership, or maybe it'll be just, oh, Simon, what did you say? And I'll just be horribly embarrassed by it all. But they took loads of stuff of all the people visiting and chatted to everyone. So it should be a good promo for Bath anyway. On the 12th, we've got the first science images, first colour images from James Webb's telescope. So that's good. And on the 13th, we have a perigee syzygy moon, the last of the year. That's a supermoon to other people. So that'll be the Buck supermoon. And on the 16th of July, the new exhibit for the Herschel 200 season is actually starting off. So there's going to be new exhibits, and then that'll be joined further down on the 25th of August by a new installation in the garden to commemorate. So that's being carved at the moment out of stone. That'll be laid in stone in early August and then revealed on the 25th of August. We've got meteor showers coming there, and Saturn is creeping back into our skies. So it's around about midnight, it's creeping all the time, and there'll be opposition on the 14th of August. So if you've got a telescope or binoculars, it's starting to be reasonable. You don't have to wake up at stupid o'clock to see Saturn. So they're going to go through, so we'll then get Neptune, then we'll get Jupiter reaching opposition over the next few months. So good targets if you missed the planets for a while. We'll be back on Wednesday, the 28th of September, and we're going to have Martin Griffiths, who looks after dark sky Wales. He's the kind of guy who goes off, he's hired by cruise ships and things, and he's like the resident astronomer on board cruise ships, but also runs lots of classes and writes lots of material, does tons of outreach, and he's going to be talking to us about asterisms, binoculars and small telescopes. So basically looking up in the sky with starter kit. So it's a great way to start off in September with more of a starters talk. So that's there. Now I have reached my get off, Simon, time. So it's time to hand over to Dr. Megan Argo. I've seen Dr. Argo sort of doing lots of presentations and all kinds of conferences, those kind of things, and very much sort of admired her from the professional context, and not realizing too much about what she was doing with the rest of her time. But she's a professional astronomer. She is a science communicator. She's doing it for 20 years or so. She's been going around and promoting astronomy, but also sort of science as well to kids sort of across the world, from Scotland all the way through to Australia. I think some of the other places she stopped in India, South Africa. Wherever she goes, she's sort of evangelizing sort of science as sort of a way forward, and a good way of thinking about stuff. What else have we got? She currently works as a senior lecturer at the University of Central Lancashire, which is based up in Preston. And you wouldn't be mistaken if you thought you might have seen her on BBC, sort of when they're talking about the latest thing in science. I think Megan's on speed dial for the BBC to talk about these astronomy things that are going on. over the COVID period, she was very generous and offered to do a online Zoom talk to the local Guys Brownies group, and then put on Facebook. Anyone else want one? And then 59 sessions later, her huge efforts, Herculean efforts, to talk to that many people, like 1,400 people, young, impressionable young women who sort of might take up science, and sort of just to enthuse them to actually think about looking up and what's beyond the skies above them. And for that, she was nominated for the British Empire Medal, and she was awarded it in the recent honours list. So congratulations, Megan. So what I'll do is I'll hand over to you, if that's okay. I'll stop my screen share, and then we can go.
Okay, thank you for that introduction. I will share my screen if I can find the right file. There we go, that one. Okay, can you see my screen?
Yes.
Excellent. Okay, is somebody keeping an eye on the waiting room? Ah, yes.
Yes.
Good. Okay. Okay.
Yep. Yep, we're ready for you.
Okay. So it's lovely to be here virtually to talk to you all tonight. I have been to the Herschel Museum, but not for quite a long time, but I have very good memories of wandering around the galleries, learning all the stuff about the music that Herschel did. I learned quite a lot when I came to visit. So yeah, my talk tonight is the next blink of a cosmic eye, astronomy in the next 200 years, and a little bit of context to where this talk came from. I was first challenged to write this talk, as Simon said, 2 years ago, over 2 years ago now, in January of 2020. And that was part of the celebrations for the 200th anniversary of the founding of the Royal Astronomical Society. At the time, I was on the council. I've since been vice president as well for the last couple of years. But we were celebrating our 200th anniversary in 2020, and we had a huge program of events planned across the year to celebrate various different aspects of the society and how far it's come. And the first ordinary meeting of the Royal Astronomical Society held in London at Burlington House in January 2020. They had 3 talks. They had Alan Chapman. If you've ever heard Alan Chapman speak, you'll know he is a fantastic speaker on the history of astronomy and the history of various different scientists in general. So he gave an overview of the previous 200 years, sort of the founding of the society and how far things have come in that time. And my challenge, my job was to follow him. Following Alan Chapman is something of a terrifying idea. I'm trying to predict astronomy in the next 200 years is even more terrifying. This is a rather ambitious talk title that I was challenged to try and write something to. And as you might expect, I'm not a futurist, right? I can predict all manner of things, but the most serious prediction I could possibly make, the most sensible one, is probably that whatever I predict, I would likely be wrong. So a slightly more realistic talk title might have been this: utterly unrealistic predictions for astronomy in the next 200 years. But we'll give it a go anyway. Now, before we go forwards and have a look at what's coming in the next 200 years, it is a good idea to stop, pause for a second, and just see how far we've come in the last 200 years. So just a few highlights of some of the things that have happened in the last 200 years in astronomy and physics. If you think about what we didn't know about physics, about astronomy, about the universe 200 years ago, the progress we've made is actually phenomenal. 200 years ago, we didn't know Maxwell's equations. We knew that there was visible light, but most of the rest of the spectrum was still completely invisible to us. So in the last 200 years, we've expanded our tools to try and understand the universe immeasurably. 200 years ago, we'd never measured the distance to anything outside of the solar system. And the image here of the 2 stars moving across the sky, you're watching the proper motion of 2 stars across the sky. This is 61 Cygni, the motion of which was, well, the distance to which was first measured by Bessel, 3.3 parsecs. And that was done in the last 200 years. So 200 years ago, just think about what that means. We didn't know the scale of anything other than our own solar system. We didn't know the scale of the Milky Way galaxy. We didn't know the distance to the other galaxies that we can see in the sky. We didn't know the nature of those other galaxies that we can see in the sky. So we have learned an awful lot about the the scale of the universe in that time. We've also detected an awful lot of planets outside of our own solar system. We now know of many, many planets around other stars, and the graphic down here just shows you how many exoplanets we now know of and their distribution in terms of how far they are away from their parent star, their semi-major axis, and the planetary mass. So again, huge step forwards in our understanding of the local universe in that case. I mentioned the electromagnetic spectrum, of course, back in the 1940s, people started playing around with radio waves to do astronomy, and that field has now grown immeasurably since the 1940s. And this is the horn here. This was what was used to actually detect the first signals that we knew were coming from the cosmic microwave background. So again, our knowledge of where the universe came from has expanded greatly in the last 200 years. In the last few years, of course, we've had the first image of a black hole, the shadow of the event horizon around a black hole. And of course, just earlier this year, we've had the first images of our own black hole, Sagittarius A star as well. And this technique is fantastic. It's superbly detailed, and it's a really complicated technique to get right. So the challenge in getting that image is not to be underestimated. And then, of course, a few years before that, we had the first detection of gravitational waves as well, predicted quite a long time ago, but only first detected back in 2016. So there are many other highlights I could have chosen. These are just some of the exciting things that have happened in the last 200 years, but that gives you some sense of what we didn't know 200 years ago compared to what we know today. The progress has been pretty extraordinary in that time, and there is no reason to think that the progress that there might be in the next 200 years will be any less extraordinary. Now, of course, just recently, we've had the first results from the data release 3 of the Gaia satellite. Now, Gaia has been in space for a few years now and is surveying the entire visible universe as it moves around the sky out at the second Lagrange point. This was released earlier this month on the 13th of June to huge excitement in the astronomical community, as any Gaia data release does actually generate a massive amount of interests. It's giving us accurate positions of stars over multiple epochs, and it's also allowing us to measure the motions of stars in the galaxy. We can accurately measure the sun's motion around the center of the galaxy, as well as the bulk motions of the stars in the different spiral arms. And there is so much information that we're getting from these data, and this is just some of the highlights from that data release 3. These are some of the highlight images that they released on the day of the data release. We've got different plots here showing different aspects of the motions in the Milky Way. So we've got the radial velocities of stars here, whether they're moving towards us or moving away from us. So you can see the motion, the overall circular motion of the Milky Way galaxy here in the disk. Now, some of those stars are coming towards us, some of them moving away from us. Down here, we've got the same velocity information, but now including that proper motion on the sky. So you can see how things are moving relative to the Earth. So how the galaxy is sort of actually, there's that warp in the disk of the galaxy, and that's kind of what you're seeing in that image. And then up here, we've got a measure of the extinction. So this is how much the light from a background star is being scattered or absorbed on its way from that star to us here on the Earth. And the darker patterns here in the center, this is where the extinction is the highest. That's where there's the most absorption or scattering. And that's showing you where the dust is in the plane of the Milky Way. That dust is a problem in the optical because, of course, it makes it harder for us to see past it, makes it harder for us to see through it, just as on a day like, I don't know what it's been like down there today, but up here it's been pretty cloudy. So today we haven't really seen the sun. So the clouds on the Earth get in the way and stop us from seeing the sun and the stars. The clouds of dust in the Milky Way have the same effect on the light coming from the stars in the center of the Milky Way. And that's one of the reasons you need radio techniques to see black holes in the center of galaxies, because radio waves can penetrate through that gas and dust. And then down here we have, this is a measure of the metallicities of the stars. So this is telling you what the chemical composition of the stars is. And it's basically showing you where there are older stars and where there are younger stars in the plane of the Milky Way. And again, there is so much information in these data that it's going to keep astronomers busy for decades to come. And it's not just Gaia. There are lots and lots of surveys underway at the moment that are generating huge amounts of information. And all of that data is being recorded, is being stored in computers. Some of it's being processed in real time, but there's an awful lot that we're going to be able to do with it later on as our computers get more advanced, as our processing speeds get faster, as our hard disks get more impressive. So there is an awful lot that will come out of these data in the years to come. So there are other missions, of course, that are underway. There are many of them. Another highlight is the Voyager 1 and 2 missions launched, not very far apart, of course. They've been traveling out through the solar system. They did the grand tour of the gas giants, and they're now way out past the influence of the sun in the solar system. So we have the sun in the center here and the orbits of the planets. You can even see Pluto there, how old this graphic is. Here is the sphere of the sun's influence. The sun has a solar wind. All stars have a wind that goes out from the surface. And the solar wind is actually blowing a bubble in the surrounding gas, the interstellar medium. And what we think from the data that are still coming back from Voyager 1 and Voyager 2, that data shows that they've now passed through the edge of that bubble, and they're actually into the bow shock, which is as the sun is moving around the galaxy, there's a bit of a bow shock, just like when a ship moves through the water, you get a wave that rises up in front of it. This is the same kind of thing as the sun moves through the surrounding, the interstellar medium within our own galaxy. So these instruments, they're still sending back data, not as much as they used to be. Most of the instrumentation has had to be switched off to save power, but they are still sending back data. So there's a lot of missions that are doing both astronomical and observations of the Earth that are ongoing over the last 40, 50 years and are still sending back data. And these are hopefully just the first of many man-made interstellar probes that we might see over, hopefully, our lifetimes, but certainly over the next 200 years. So that's a very brief look at how far we've come in the last 200 years, and very, very brief out of necessity, because there's an awful lot to get through yet, as you might imagine. The main thrust of the talk is, where are we going in the next 200 years? And there's a lot of directions I could have gone with this talk, but when I was sitting down thinking about what on earth I was going to write about in trying to predict the next 200 years, the first thing that came to my mind was that reusable rockets. We now have reusable rocket technology, so rockets that not only launch stuff into space, but the rocket itself comes back, lands, can be refitted, refilled, and launched again. And that makes space travel and getting satellites into orbit much, much cheaper and potentially much, much faster. The development cycles for a lot of space-based equipment in the last 50 odd years have been very, very long, James Webb included. If we can do missions on a shorter, faster, cheaper basis, then potentially we've got a lot of interesting avenues for doing astronomy there. So I think this is potentially a really exciting thing for astronomy. But as I said, this is quite an ambitious talk, and it's something of a personal talk, something of a more personal talk than I would usually give. And that's kind of intentional, because, as I said, if you'd asked any other astronomer to write their predictions for the next 200 years, you probably would have got a different set of opinions. So this is my view of what I think are the particular missions that are worth watching in the next few years, and what I think are the most exciting things that are going to come in the next sort of few decades, and where they might take us in the more long term. As I say, if you'd asked any other astronomer, you might have got slightly different opinions. But it is an ambitious talk. So for some inspiration, when I was sitting down trying to come up with ideas, I did what an awful lot of astronomers, certainly of my generation, would do when they want some inspiration, is that I asked Twitter. So I went to Twitter and I asked all the people that follow me on Twitter, I said, what do you think might happen in the next 200 years? And this is what they thought. So this is a word cloud made up of the responses that I got when I asked my Twitter followers to what they thought was going to happen in the next 200 years. And you can see what kind of things they were interested in. A lot of people, the bigger the word in this word cloud, if you're not familiar with word clouds, the bigger the word, the more times it cropped up in people's responses. So life features very, very prominently in the middle of this word cloud. A lot of people are either hoping that we will find evidence of life, or in fact life itself, or hoping that at least we're going to carry on searching for evidence of life, at least in the solar system. But there are a few other things as well. People are hoping that we'll make a manned return to the moon, we'll send people to Mars. You can see that there's a lot of excitement over discovering aliens, telescopes on the moon, dark energy. It would be nice if we can discover exactly what dark energy is and what it's doing to the universe. Betelgeuse features quite prominently. Again, we'll talk a little bit about Betelgeuse later, but Betelgeuse in early 2020 was the topic of conversation in tea rooms and astronomical departments around the world. And then there is Starlink. Okay, so Starlink, the satellite constellation, there are some challenges in here as well. And we'll look at all of these things as we go through. So there are definitely some common themes here. So when I was putting the talk together, I basically took this word cloud and said, okay, how do the telescopes and the planned missions stack up against what this random selection of people who happen to interact with me on Twitter, to what they think and hope about the future of astronomy? So as I say, I've selected a few projects that I think are particularly exciting in response to this word cloud. Other opinions are, of course, available. So the first one I want to talk about is ExoMars. Now, ExoMars is a mission that I have, again, some very small personal involvement with. We've had Perseverance, we've had Ingenuity, we've had a lot of missions to Mars in recent times, and they're sending back some really, really interesting data. And of course, the Chinese mission as well. ExoMars is just another Mars mission, right? This one I had a tiny involvement with. When I was an undergraduate, I was lucky enough to do a summer project in Australia at the Anglo-Australian Observatory, as it was back then. And I was part of a team in the instrument science group that were pitching a new instrument. It was in the planning stages at that time. And they were pitching a particular instrument to the project. It didn't get selected. If it had, I think my career might have gone in a slightly different direction. But I do have a little bit of interest in this mission. Like many of the other Mars missions, the rover is going to take soil samples, going to drill into the rocks and take rock samples and look for evidence of, yes, evidence of life, but evidence of surface processes as well, and look at some of the geology of Mars. But it's going to work in combination with an orbiter that's already in orbit around Mars. This is the Trace Gas Orbiter, and it's actually already been in orbit around Mars for a few years now. And its job is to look for the traces of gases that may be produced by biological processes in the Martian atmosphere. So it's characterizing the Martian atmosphere in much better detail than we've ever had before, looking for those things that might have been produced by biological mechanisms and seeing if it can localize them. And then the rover, the idea was to go and then test on the ground those sources of those particular chemical compounds. Unfortunately, this rover has been significantly delayed. It was originally scheduled for launch many, many years ago. That got delayed and delayed and delayed. And then it was scheduled for launch in 2020. But because of COVID and the difficulties of getting things integrated in a clean room under COVID conditions, it got postponed to 2022. The launch window is in September. Unfortunately, the war in Ukraine has kind of put a stop to that because it was supposed to fly on a Russian rocket from Kazakhstan. So this mission at the moment is essentially permanently in mothballs. We don't know. It's certainly not going to launch this year. It may not launch in the next launch window, which is in 2 years' time. So we don't know when this mission is going to go up. It's actually unlikely, according to ESA, it's unlikely to happen before 2028, unfortunately. So this is a mission that's been a long time in the planning. I was in Sydney in 2003, so that shows you how long it takes from the drawing board, from the mission planning to actually getting to Mars. So this is one to watch, but maybe not for another decade yet, unfortunately. There's plenty of other exciting solar system stuff going on though. Another one to watch is JUICE, the JUICE mission. This is going to the Jupiter system. And the idea is it's a large ESA mission to explore Jupiter, its icy moons, and the interaction between those moons and Jupiter itself. It's going to overlap with NASA's Europa Clipper mission. So Jupiter is going to be an exciting place to be for spacecraft in the next sort of couple of decades. It's not going to arrive until 2031, so it's going to take a while before it gets there. After a launch, hopefully next year in, I think, April, it's currently slated for. When it gets there, it's going to probe several of Jupiter's moons in detail. So it's going to look at Europa, look at the composition and surface geology, looking for pockets of liquid water under the surface. It's going to do flybys of Callisto to look at, and again, see if there's any evidence of water under the surface, but then to move into a position for capture around Ganymede, into Ganymede's orbit. And Ganymede is interesting because it's the only moon, certainly the only moon around Jupiter, that we know has its own magnetosphere. So it has a magnetic field. Most of the orbits, most of the moons that we know of do not have a molten core, therefore they do not have a magnetic field, but Ganymede does. So one of the things that this probe is going to do is look in detail at Ganymede, its magnetosphere, and how that magnetosphere interacts with the magnetosphere of Jupiter itself. Because again, that's something that we don't know very much about. So that's going to be a really, really interesting mission to watch. When it gets towards the end of the mission, after it's done all its detailed measurements and it's done its surface mapping, it will start to run out of fuel. It won't have enough fuel to leave Ganymede's orbit. So when it reaches the end of mission, it will basically come in for a grazing impact on the surface of Ganymede. As it does so, of course, it will take very, very close-up images of the surface on its way in. But this is definitely going to be an exciting mission to watch. So, and it's going to go on for again, many, many years once it gets to Jupiter. So expect lots and lots of fantastic imagery of Jupiter when it does so. So that's some of the solar system highlights. Of course, there's plenty of astronomy highlights as well. And one that's already been mentioned this evening is the James Webb Space Telescope. Now, of course, when I wrote this talk, James Webb was nowhere near launch yet. Now we actually have images of the thing in space. This is the little video, of course, from just after launch when it separated from the rocket fairing. This was the last view that we had of the James Webb before it disappeared off towards the second Lagrange point. This is an infrared telescope, and it's going to be fantastic, and it's going to be really exciting. And yes, I am going to be watching the press conference on July the 12th because I can't wait to see those images. But again, showing you the time scale it takes, the time it takes to get something like this into orbit. The development on this particular telescope began in 1996. So that's the sort of timescales we're looking at for these big missions. That's how long it takes to get something from the drawing board to actually get off the ground and into space. But it did eventually launch on an Ariane 5 from French Guiana on Christmas Day last year. I watched it. It kind of it was more exciting than Christmas Day lunch. But there you go, to an astronomer, of course. So why is it such an exciting telescope? Well, it's half the mass of the Hubble Space Telescope. Hubble, of course, has been in space for over 20 years now, but it's got 5 times the collecting area. And of course, the more collecting area you have, the bigger your telescope, the bigger your light bucket, the more light you can collect and the fainter the objects that you can see. And that's really important for James Webb because its scientific goals are to study things like the processes of star and planet formation in the Milky Way. We know that those processes happen in cold, dense clouds in the plane of the Milky Way. Remember that image I showed you earlier of the extinction that you get in the Milky Way from the Gaia data. That extinction is those clouds of cold, dense gas and dust that are forming stars and planets. Now, to see them optically, you see what's going on, is it impossible? So you need to study that star formation. You can only really study it in the infrared and in the radio. So the James Webb Space Telescope is going to let us peer into those really dark, dusty clouds in the center of the Milky Way and see what is happening in that process of star formation. There's an awful lot we don't understand about exactly how stars form. It's also going to help us do things like study the formation of the very first stars and galaxies in the early universe, not long after the Big Bang itself. Again, we know that stars and galaxies formed because we see them in the universe today and going way back into the history of the universe, but we don't know exactly when or exactly how those first stars and galaxies formed in the early universe. And that's another thing that hopefully the James Webb Space Telescope is going to give us information on. So there's a huge amount of really interesting science that's going to come from this mission, and hopefully it's going to be fantastic. So what is the status of it right now? Well, this is a screenshot from the JWST website at NASA just the other day. This is showing you the current status of the mission. So this is the timeline on the bottom, and it shows you from launch going all the way up to now. This is where we are now. So we're at something like 26 weeks post-launch. And we have most of the instrument commissioning has been done. An awful lot of the telescope has been checked out and is now properly functioning, which is fantastic to see. And this graphic here shows you the temperatures on the different sides of the spacecraft. And this shows you why it has that enormous, great big sun shield at the back, that thing that's bigger than a football pitch. The reason it has that sun shield is to protect the instrument, all of the delicate electronics on board, and the telescope itself from the heat given off by the Earth, the Moon, and the Sun. And you can see on the back here, this is the side that faces the Earth and the Sun and the Moon. You can see parts of it are at 49 Celsius. This is pretty hot for an infrared telescope. To get the best detailed images of the sky in the infrared, you want your receiver as cold as possible, which is why you need this sun shield. It protects it, it reflects a lot of that heat away and absorbs some of it and protects this side. So this side of the spacecraft, the cold side, you can see it's much, much colder on this side, and that's necessary for all those infrared instruments to work properly. Now, of course, we know the first images are coming very, very soon. If you want to watch them, that's the easiest website to go and have a look at. That's the shortest URL I found to find it. But there is now a countdown on the NASA website. This isn't live, of course, because I couldn't put a website in my talk. But this is from just before we started this evening, showing you how long we've got to go until those first images. And yes, there are an awful lot of astronomers, even astronomers like myself. I'm a radio astronomer. I'm still excited to see those first images because we know they're going to be good. The mirror was recently impacted by a very small rock. You might have heard the this in the media. It certainly made the BBC news. A small rock hit one of the mirror segments. You can see a sort of stylized version of the mirror segments here. Each of these hexagonal segments is a mirror that can be adjusted in several angles to make it line up perfectly so the telescope works. That little space rock, that little meteorite, actually hit one of those segments and has damaged it slightly. It's not going to affect the overall image quality, and most of the effects that it did will be able to be corrected for in the software pipeline that deals with the data. So it's not going to be a big deal. And in fact, the telescope was designed to cope with impacts of micrometeorites, because it's not a shielded telescope. They knew this was going to happen. So it's not a disaster. And the first images, yeah, should be really, really exciting. But there are lots of other telescopes as well. It's not just James Webb. James Webb is the next one that will come online, but there's plenty of other exciting telescopes as well. Some of them space-based, but some of them ground-based as well. So let's have a look at some of the exciting upcoming ground-based telescopes. So James Webb's an infrared telescope. On the ground, we have the Vera C. Rubin Observatory, which is under construction at the moment. This is a very large optical telescope whose aim is to survey the sky rapidly, in the same way that Gaia is scanning the sky repeatedly and adding the data together. The Vera C. Rubin Observatory will do the same thing from its position in Chile, so it won't be able to see the whole sky, but it will be able to see quite a lot of the sky. But it will do it much more quickly than Gaia will. So the Vera C. Rubin Observatory will be able to survey the entire sky from its location, as visible from its location, roughly once every 3 days. That's a huge amount of data. How can it do that? Well, it's got a big mirror, 8.4 meters primary mirror. Again, that makes it very, very sensitive. It's got a short focal length, which gives it a nice wide field of view, and its field of view is actually 3.5 degrees across, and the moon is 0.5 degree across on the sky. So that gives you some sense of scale of just how big the field of view of this instrument is. To cover that field of view, you need a very big camera. So the camera itself is a 3.2 gigapixel camera made up of 189 individual CCD chips, all stacked together. So this is a phenomenal telescope. It's going to give us a very, very fast, rapid survey of the sky across several different filters in the optical part of the spectrum. Why on earth do we want to do this? Why on earth do we want to take images of the sky once every 15 seconds and generate, 1.3 petabytes of data per year? What are we going to do with all that data? Well, the reason we want to take all of this data is partly to look at structures in the universe. This will give us, if you add all of the data together, you end up with a very, very deep survey of the sky. And that is going to be good for letting us look at the structures, the large scale structures of the universe, the distributions of galaxies in 3 dimensions that we see in the universe. And again, that will tell us about something about how the universe formed and how it's evolved to what we see today. It's also going to give us an awful lot of information on things that are moving on the sky. So it's going to be fantastic for looking at things like asteroids moving around in the solar system. It's going to enable us to detect much, much fainter asteroids across large parts of the solar system than we have been able to date. So it's going to give us a much better census of the distribution of rocks in the solar system. It will allow us to model their orbits as well, and potentially spot anything that may be Earth crossing in the future. So anything that might potentially be a threat to the Earth in the future. It's also going to let us detect transient optical events as well, things that appear and then disappear over maybe days, weeks, months, but it will also enable us to look for new types of transient events. So we know there are transient events like novae, supernovae, and so on. But this is a new capability. We haven't had the capability to survey the sky to this depth, this fast before. And one of the exciting things about astronomy is that every time we get a step forward in technology, we start to be able to do something new that we couldn't do before. Often we start to discover things that we didn't know were there to be predicted before. So one of the hopes with this telescope is actually it might show us new types of transient that we've not seen before, things that are changing on short timescales that previously we just didn't have the sensitivity and the repetitive capability to detect. So again, this is going to generate a huge amount of data that will keep astronomers busy for decades to come. So that's in the optical. As I said, I'm a radio astronomer, so I can't give a talk without mentioning at least one radio telescope. And the radio telescope that's on the horizon in the part of the spectrum that I work in is the Square Kilometre Array. This is the next generation radio telescope, and it's so big and so complicated and covering so much of the radio spectrum that actually it needs more than one type of antenna technology. So we have SK high, well, SK mid, which is these sort of dish antennas here, the more traditional looking radio telescopes that you might think of. And then SK low is these sort of ground plane arrays down here, sort of fields of dipoles that sit on the ground. They actually look a little bit like Christmas trees when you look at them up close. They look a bit different to what you might expect for radio telescopes, but they let you survey the low frequency part of the sky. Now, the original image that came from the SK organization had an optical picture of the Milky Way in the background. I thought that was a bit daft because that's not what it's going to see. So I photoshopped it out and added in instead a radio view of the Milky Way. So this is what you would see if you had radio eyes and you look towards the center of the Milky Way. This is what you would see in the sky. So this is the plane of the Milky Way goes across in this direction, and down here, in the middle of all of this mess here, this is where Sagittarius A star lives, right in the middle of this bright blob here. So there's a lot of really interesting things that we can see in the radio sky that, again, because of that dust extinction that I showed you in the Gaia image earlier, you can't see in other parts of the spectrum. To see into the middle of the galaxy, you have to look in the radio because it's the only thing that's powerful enough to see through all of that gas and dust and show us what's going on in the center. It's a very, very powerful telescope. It's going to be a very powerful telescope eventually. So phase 1 is the only part that's funded at the moment. That will be a good telescope. Phase 2 will be even better, even bigger, even more powerful, but that isn't even yet funded. So that is decades into the future if it happens at all. So what are the science goals of the Square Kilometre Array? Well, aside from giving us a fantastic view into the center of our own Milky Way, it's going to let us look at galaxy evolution and cosmology. So studying, again, the evolution of galaxies, going back to the early stages of the universe, not long after the Big Bang, allowing us to see, again, those very first stars and galaxies forming. It's going to let us do strong field tests of gravity using pulsars and black holes. Again, something that you can't do in any other part of the spectrum. You have to do it in the radio because that's where these objects are brightest. It's also going to help us look at the origin and evolution of cosmic magnetism. We know that things like the Milky Way have magnetic fields running through them. We don't know the origin of those magnetic fields. So again, that's something that the Square Kilometre Array is hopefully going to help us look at. So you might notice a bit of a theme here. A lot of the science cases are similar. All of these telescopes that I've talked about want to allow us to look back and see the formation of the first stars and galaxies after the Big Bang, and allow us to see the evolution of the universe from those early galaxies to what we see today. So why do we need all these different telescopes? Well, the reason is that if we've got only one type of telescope in one part of the electromagnetic spectrum, we're only seeing part of the picture. To understand the physics of what's going on, we need to look across all the different parts of the spectrum, because each part of the spectrum, whether it's radio, infrared, optical, X-ray, they tell us different bits of physics, different aspects of what's going on physically in these different regions of space. So by combining information from all of these telescopes together, we get the most complete picture of the universe possible. So individually, these telescopes are powerful, but together they're even more powerful. So I've shown you some of the exciting missions and instruments that are on the horizon, and there is going to be a huge amount that is discovered in astronomy in the next few years to the next few decades, and that's for certain. But it's not all rosy. There are some significant challenges on the horizon as well, and one of them came up quite prominently in that word cloud from people on Twitter was the problem of Starlink satellite mitigation, more generally speaking, because it's not just Starlink. This is an image of a train of Starlink satellites. You can see the dashes going across the image here. This is one of the very first launches of a Starlink for the Starlink constellation from a professional observatory in Chile. This was 19 satellites affecting the field of view from this site for about 5 minutes. Now you might think, well, that's not much of a problem, is it? But imagine you're observing with the Vera C. Rubin telescope. You're trying to observe the entire visible sky every 3 nights, and your telescope has a 3.5-degree field of view and is looking for things that are transient. And these satellites are this bright. This is a significant headache. This is the kind of thing that they're going to be seeing. This is an image from a different telescope. This is DCAM, which is a similar sort of thing. It's a wide field telescope with lots of CCDs making up the focal plane. But you can see again these diagonal streaks here. These are Starlink satellites that went through the field of view while they were taking this observation. It's a problem for DCAM because DCAM is looking at the structures and distributions of galaxies, very faint galaxies in the distant universe, if your images are affected by satellites, your image is completely wasted. You have to, take another image. So the more satellites go into space, the harder this kind of observing gets, the more difficult it's going to be. Why is this a problem? Well, SpaceX have launched over 1,000 satellites already by mid-2021, and they've got tens of thousands approved. And there are other constellations as well. This is an animation that's a couple of years old now, but it's an animation from AGI that shows you the scale of the problem. This is going from 2017, before Starlink started launching. And you see the Iridium constellation, and then you start to see SpaceX satellites being launched. And then 2020, OneWeb starts going up. You've got lots of other constellations coming into the picture as well, and it just accelerates. Now, as I say, this was made a few years ago, so this was using the constellations that had been given approval at the time the animation was made. More companies since have come forward with their own plans for constellations, so actually the reality is worse than what you're seeing on the screen right now. But again, this gives you a scale, an idea of the scale of the problem that astronomy and anyone who wants to observe the sky is potentially facing. So there are going to be hundreds of thousands of satellites in the sky. And again, to give you a bit of context, across both hemispheres, with the naked eye, under good conditions, you can see a total of about 10,000 stars. So if we've got hundreds of thousands of satellites in the sky, they're vastly outnumbering the number of stars that we can see without a telescope. Now, of course, it's not all bad news. There are very good reasons for putting these constellations up there. They're going to provide universal internet access for anyone that can afford them anyway, and it will be useful in many parts of the world. But it is a huge headache for astronomy, and not just in the optical either. Each of these satellites is warm, so it's going to be a problem for any infrared telescopes on the ground. They're also transmitting data, and they transmit data in the radio. And existing satellite constellations, Iridium is a particular bane of radio astronomers' lives, but all of these constellations are going to add to the radio noise. And a satellite shining a beam down your radio telescope is not much different to somebody shining a floodlight down your optical telescope. It's the same kind of effect. You completely swamp anything that's coming from the universe. So we're going to have to deal with this somehow. But how do we get around that? I say it's not all bad. Of course, there are many, many good reasons for doing this. They can help us address several of the, if not all of the UN Sustainable Development Goals. And they can be extremely useful in natural disasters, for example. Satellites provided vital communication during the Tonga volcano just recently, and also during the Ukraine war. Starlink sent terminals to Ukraine to allow them to keep internet access when Russia were trying to cut that off. So there are very good reasons for doing this, but the sheer scale of how many constellations we've got up there is definitely going to be a problem. And it's not just a problem for astronomy, it's a much wider problem as well. It's a problem for anybody in space. This is a graphic taking data from the UN Office for Outer Space Affairs, and I updated this graphic just last week. So this is launches to June this year, and you can see going back all the way back to 1957, the green bars are launches per year, and the blue line is cumulative numbers of launches. So going up to 2022 at this end. So you can see that just in the last couple of years, the number of launches per year has just skyrocketed, and that's largely down to these satellite constellations. According to the UN Office for Outer Space Affairs, there are currently nearly 9,000 satellites in Earth orbit, but less than half of those are actually operational. A lot of them are old satellites that have been there, some of them since the 1960s. Many of them are defunct, they've run out of power, or they failed for some other reason, and they haven't yet come close enough to the Earth's atmosphere to deorbit and come back to the ground. So there's an awful lot of space junk in low Earth orbit. So since the 1950s, we've launched more than 12,000 objects into space. And there are, according to the NASA office that monitors space debris, the current estimate is that there are over 23,500 objects larger than 10 centimeters in size currently orbiting the Earth. 23,500. That's an awful lot of space junk. And if you've seen the film Gravity, you might have some idea of where this potentially could be going. This is a screenshot from the film, and of course this is fiction, but it's based on a real idea. It's based on the idea of a chap called Kessler. He came up with this idea, and it's been called Kessler syndrome ever since. The idea that if you have a collision in space, it generates debris, but that debris is moving fast at kilometers per second. And if you've got enough of that debris and there are enough objects in orbit, that debris can go off and hit other satellites, which then disintegrate and cause more debris, which go off and hit more satellites, causing yet more debris, and they cause a cascade effect. And the ultimate eventuality for Kessler syndrome is that the Earth ends up encased in a field of fast-moving debris that becomes unsafe for us to launch through. And at that point, we lose all of our internet access through satellite technology. We lose an awful lot of our banking infrastructure because most of our financial transactions go via satellite these days. It potentially is a huge headache for the whole of our modern way of life. So this is potentially a real problem. Now, of course, Kessler syndrome is hopefully a very, very long way off. Hopefully it will never happen. But there are cases where there are jumps in the numbers of debris, and we see a few of them here. This is another graphic from NASA, again, a couple of years old now, but you see this line here shows you the amount of fragmentation debris, and you can see that there are spikes here at certain points in history. This one here, this spike, this is the total number of objects in Earth orbit. This was the deliberate destruction of a Chinese satellite. This jump in the number of objects was the accidental collision of two satellites. Now, there have been more jumps since, because in December last year, there was an accidental collision between a Chinese meteorological satellite and some rocket debris from a previous launch, creating yet more debris. And then there was also a Russian anti-satellite test to a deliberate destruction of a satellite back in November last year that created 1,500 pieces of debris, and actually was a serious risk to the astronauts on the International Space Station. They actually had to take maneuvers to avoid the debris field. So this is a serious problem, and it is only, I'm afraid, going to get worse. So with satellites affecting our view from the ground, and low Earth orbit becoming an increasingly dangerous place to put a telescope, should we be looking around for other options for astronomy going forward? Well, people are seriously thinking about putting telescopes on the moon. This is an image I put together back in 2009. I wrote a sort of tongue-in-cheek blog post about putting a radio telescope in a crater on the far side of the moon. This is the Arecibo radio telescope, the telescope in Puerto Rico that sadly failed catastrophically just recently. One of the wires failed and the receiver assembly came crashing down into the dish. But it's a low maintenance telescope. It's simple. It doesn't have many moving parts. So it's the ideal kind of telescope to put on the surface of the moon. So in 2009, it seemed like crazy idea, but now with all the satellites going into space, actually it seems like a much more sensible idea. And in fact, there was a conference, again, like many things COVID related, this was postponed. This was scheduled for March 2020, a conference of astronomers looking at what kinds of telescopes, what kind of science we could do from the moon, and practical ways we could actually do this. Now, that again, this was postponed like much else in 2020, but the authors of the presentations that were supposed to be given at that particular conference wrote up their talks instead, and it became a special issue of the Proceedings of the Royal Society. So if you want to go and find out what people's ideas are for putting telescopes on the moon, I'd encourage you to go and look up that particular publication. More recently, there have been some conferences. Again, these were originally planned to be held on La Palma. It ended up being entirely virtual. There's actually now been 2 of these meetings, the Dark and Quiet Skies for Science and Society. So this was a big conference organized in conjunction with the UN Office for Outer Space Affairs, looking at how we can protect the skies for all parts of the spectrum, but also for humans in general as well, you know, not just looking at satellites, but looking at the problem of light pollution more generally, and the fact that so many people now can't see the Milky Way from where they live. So there's a huge number of topics covered at this week-long conference, and again, the proceedings were all there. You can go and have a look at the conference book if you're interested in the things that were discussed. But there's a real sort of enthusiasm amongst the astronomical community at the moment to try and do something about this, and they're working with all kinds of organizations to try and find ways to mitigate some of these problems. So there is hope. It's not all doom and gloom. So other places we might want to put telescopes, is it worth looking further afield, not just on the moon, but further out into deep space? You might think the further from Earth, the better. And in some ways that's true. But the further you put your telescope away from the Earth, the harder it is to get the data back for the astronomers to actually then do something with it. This is the Argus array from Star Trek Deep Space, The Next Generation. Of course, this was a subspace telescope, not an electromagnetic spectrum telescope. Subspace signals travel faster than the speed of light. Not quite sure how that's physically possible, but in Star Trek it is. So that's not something that we've discovered yet. Maybe we'll discover that in the future. But as I say, data is a bit of a problem. So is it daft? Is it purely science fiction? Well, no, we are actually putting telescopes further out into space as well. And one of the reasons for doing that is gravitational waves. I mentioned gravitational waves at the beginning because we had the first detections of gravitational waves just in the last few years. But the gravitational waves, they're not electromagnetic waves. These are actually waves, these are ripples in the fabric of the very fabric of space and time itself. But they have different wavelengths. So just like the electromagnetic spectrum ranges from long wavelength radio waves down to very, very short wavelength gamma rays, the gravitational wave spectrum goes from very, very long wavelength gravitational waves through to very, very short gravitational waves. And each of those different parts of that gravitational wave spectrum probes different types of objects, different types of interactions in the universe. So if you want to study some parts of that spectrum, then you need to build a telescope that's capable of detecting gravitational waves of those wavelengths. So the ones that we have at the moment, we have terrestrial interferometers. And those are very good at letting us find mergers of compact, low mass binaries. That's what they're very, very good at. If we want to study the interactions of binary supermassive black holes, the ones that we think are in the centers of pretty much every galaxy has a central supermassive black hole. When galaxies collide, their supermassive black holes will eventually coalesce as well, generating huge amounts of gravitational wave radiation as they do so. But if we want to study those, we need to look at longer wavelengths. And one of the ways we have to do that is to build a much, 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 much bigger telescope with much longer baselines than we can do physically on the Earth, because basically the wavelengths are bigger than the diameter of planet Earth. So we do that by putting our telescopes in space. And this is the LISA telescope. This is a planned telescope that will be in orbit around the sun. So it'll trail the Earth in our orbit around the sun. And it will consist of 3 satellites that basically shine laser beams at each other. And they very accurately measure their relative positions. And as these gravitational waves pass through the solar system, they will move the satellites at different rates as they bob up and down in the fabric of space-time. And those very, very slight differences in their relative positions will be measured by those laser beams. And that information will allow us to reconstruct the gravitational waves that are passing through the solar system. This is scheduled for launch in the 2030s, but we've already launched a test satellite just to check that the technology works. And the test satellite worked far better than the specifications. It actually performed phenomenally well. So we know this is technically possible. So 2030, watch out for the launch of LISA. This is going to be a really exciting mission. So other longer term predictions. So where do I think some of the other topics I've talked about are going in the next 200 years? Well, one of the sort of no-brainer predictions I could make is that we will find more exoplanets. I already showed you that we have discovered quite a lot of exoplanets in recent years. This graphic is showing you the scale of our discovery of planets. So down here, we've got the year is counting up here, and you can see the different planets appearing on the plot as we go through the year. So you can see that for a long time, we only knew of the planets in the solar system. Then we get to the late 90s, and we suddenly start finding exoplanets, and then it just accelerates. And again, as our techniques get better, as we understand how to do this better, and as we discovered more techniques for finding those exoplanets, and built new instruments to go looking for those exoplanets, the numbers have shot up. Again, this is a couple of years old now. The chap who made this figure, Hugh Osborne, he made this animation. He was a PhD student at the time. I think he was a little bit miffed. This image has had far more references and citations than his actual PhD thesis, but sometimes that's the way it goes. So this shows you, I'll play that again just because it's fun to watch, but this graphic up here shows you the same information just in bar chart form. And again, the different colors here are showing you the different detection techniques, the different methods that we use to find those exoplanets. So you can see that, you know, it's increasing dramatically. And if you sort of draw a line of best fit in here and you extrapolate that curve up for the next 200 years. How many exoplanets would we know of by 2022? And a very crude extrapolation at 22, I'm sorry, a very crude extrapolation of those numbers suggests that by 22, we will know of over 21 million exoplanets. Now, I think that number is rubbish. I'm not claiming that as a solid prediction. It's just showing you how fast we are currently discovering these new exoplanets. The numbers are highly uncertain, but what is 100% certain is that numbers will increase quite dramatically. We already know of 5,000 confirmed exoplanets just within the local part of the Milky Way galaxy. The more stars we look at, the more of these exoplanets we're finding, and there's no reason to think that other galaxies are significantly different to the processes that have gone into forming stars and planets on our own Milky Way. So it's likely that the universe is full of planets. Now, another longer term prediction, again, I mentioned this in brief earlier on, but in the early part of 2020, the topic of conversation in tea rooms at astronomical institutes around the world was Betelgeuse, and the topic of, will it explode or won't it? Is it preparing to go bang? Is it about to explode as a supernova? So I'm assuming you guys do know this guy because you do all this outreach. That sounds fantastic, by the way. I'm really impressed with how much outreach you guys do. But this is Orion on the sky, and this is a picture taken from Alston Observatory, which is the University of Central Lancashire's observatory. This is what our undergraduates get to use, and in here we've got an 80-centimetre telescope, which is really nice. You can see the lights here. This is not Preston. Preston's the other side of a hill, so actually the light pollution there isn't too bad for that part of the world anyway. But this is Orion, and what you see up here, this is Betelgeuse, and in early 2020, late 2019, early 2020, it had faded quite significantly, and there was an awful lot of excitement about whether this was the precursor to this thing exploding as a supernova. It's the type of star that will someday explode as a supernova. It's a red supergiant. It's one of the 10 brightest stars in the sky. It's more than 11 times the mass of the sun, and massive stars have short lives. When they reach the end of those short lives, they do explode catastrophically as a supernova. And in the 3 months from October 2019, it dimmed by a whole magnitude, which is a factor of 2.5 in brightness. So this thing did get significantly fainter. Even to the naked eye, you would notice it. If you knew Orion, you'd look and you go, something's peculiar about Betelgeuse there. Now, I, again, took to Photoshop and did a little bit of an artist's impression of how bright this thing might look when it explodes. And in fact, it will be bright enough to see during daylight. That's how bright this thing will be when it explodes as a supernova eventually. The outer layers will then expand and become a supernova remnant. This is artistic license. It won't look this big. Even if it exploded tomorrow, in our lifetimes, it will never look this big and this bright from the Earth. But if I'd done it to scale, you wouldn't see it. So this is a little bit of artistic license. But it's now back to normal brightness. So what on earth was happening? Well, actually, it looks like there was a large amount of dust production going on in the outer layers of the supernova. So there was actually a combination of effects, we think. And again, this has been observed by a combination of using infrared observations, optical observations, and radio observations as well to get that full picture of the physics about exactly what's going on. And this is the Beetlebot. If you're on Twitter, you can follow Beetlebot, and it tweets graphics showing, you know, the recent behavioral changes in Betelgeuse. And you can see that recently on May the 9th, it was 112% of its nominal average brightness. So it varies naturally anyway, but that particular dimming in early 2020 was unusual and was significant. Now, we don't know if it's going to explode in the next few years. It might explode in the next 200 years. It might explode in the next 600 years. It might not explode for 100,000 years. But at some point in the future, 100% for certain, this star will explode as a supernova. So I don't know about you, but every time I go outside and have a look in the winter sky, I do have a look and see, is Betelgeuse still there? Because you never know. When it does go bang, it's going to be the object that everybody points their telescopes at, because it will be one of the closest supernovae we've ever seen from the Earth, and the only one that will have happened in modern times with modern telescopes. So this will dramatically improve our understanding of supernova explosions when eventually it goes bang. Come on, Betelgeuse. So I'm going to skip over that. We've already talked about Gaia. So I think my almost final prediction is the safest prediction I could possibly make, is that I've talked a little bit about this earlier, and that to study the universe as fully as possible. We really want our telescopes to cover as much of the electromagnetic spectrum as possible. And now we have gravitational waves as well as another window on the universe. But one of the key things about astronomy, and again, as I mentioned this briefly earlier, is that every step forward in technology, every step forward in observational capabilities has led to discoveries that we could not have predicted. It's led to us seeing more about the universe than we could have possibly known was there to be predicted in the first place. A lot of telescopes, they're designed for a specific purpose. They're designed to look at a particular type of object to help us understand that particular type of object or do a particular type of survey. An awful lot of the time, those telescopes end up being remembered for something that wasn't even known when they were first designed. So our understanding of the universe is often driven by these new capabilities, allowing us to discover things that we didn't know were there. So at the moment, it's a really exciting time for astronomy because we have the capability to do deep observations with multi-wavelength and now multi-messenger with this combination of electromagnetic and gravitational wave observations, as well as the time domain stuff, looking at things that are changing on short time scales. That will lead to new discoveries. It's inevitable. It always does. Every step forward in technology always leads to that sort of thing. But looking forward for the next 200 years, it's really important that we keep that multi-wavelength and multi-messenger coverage. And this comes back to what I was saying about the reusable rocket technology. If we can avoid Kessler syndrome, if we can avoid filling up low Earth orbit and having lots of collisions, then that cheaper, smaller rockets that allow us to launch things quickly will hopefully allow us for the future to keep that multi-wavelength capability, because some of these parts of the electromagnetic spectrum, of course, you just can't do from the ground. You have to go to space in order to do them. So cheap launches make that a real possibility going forward and looking forward to the future. So I think the future of astronomy is certainly very, very exciting, and I can't wait to see what we discover next. Now, I said that was my almost final prediction. My final prediction is a slightly tongue-in-cheek one. And again, this made perfect sense to predict this 2 years ago in January 2020 when I first wrote this talk. And that was that by the 400th anniversary of the Royal Astronomical Society, or by Astrofest 2220, instead of all meeting physically in a room, we'd be meeting by hologram. And of course, you know, less than 3 months later, we had the pandemic and everybody got very familiar with tools such as Zoom and so on. So this prediction came true a lot sooner than I had anticipated. Somebody also pointed out that possibly in 200 years, London would be underwater, so we wouldn't be able to have meetings at the Royal Astronomical Society or Astrofest in London anymore because London would be underwater. Let's hope that doesn't happen. We need to fix climate change, but hopefully that won't be happen. But I do think that hopefully going forward from the pandemic, we will make better use of things like Zoom for meetings that otherwise in the past, you know, a lot of conferences happen around the world that don't really need to happen in person. We don't need to fly around the world to have a meeting. We could do things much more efficiently and with a much smaller carbon footprint. And we're all now used to the tool. So hopefully, looking forward, astronomy will take that on board and will improve our carbon footprint, because a lot of astronomers going to observe in various parts of the world do fly a lot. So my hope is that we will learn from the pandemic and we'll do things better for the future. But with that, I will bring it to a close. Thank you very much for your attention. I hope you've enjoyed my thoughts on where we're going in the next 200 years, but I will leave it there. Over to you. What do you think is going to happen in the next 200 years? Thank you.
Thank you, Megan. Excellent, Megan. What questions do people have? Oh, yes, Prim.
Thank you, Megan. That was a really, really interesting talk.
Can I ask, if you're going to ask a question, can you come a bit closer to the laptop? Because I can't quite hear you.
Theory. This mic should help.
Ah, cool. Thank you.
Hi, thanks, Megan. That was a really interesting talk. Really enjoyed that. Could I just ask, do you think there's going to be anything that's going to help us understand dark matter, dark energy at all that's in the next sort of 200 years? Sooner?
Yeah, that's a really good question. I mean, it's one of the sort of embarrassments, if you like, about astronomy in the modern age is that so much of the universe we don't really appear to understand at all. There's more there than we can see, and the vast majority of the universe is invisible and we don't know what it is, and that is a big problem. There are a lot of people working on that problem. So there are a lot of large-scale cosmology surveys actually studying the structure of the universe that are hoping to shed some light on the nature of dark energy. But there are some fundamental physics experiments going on as well. So the kind of things that are happening at the Large Hadron Collider that are hopefully going to at least eliminate some of the candidates for dark matter, if not discover what dark matter is. It's not a field that I know a huge amount about. That's a long way from my specialism. I study galaxies. I study individual galaxies and their constituents rather than that sort of thing. But yeah, certainly there's a lot of work going on in that area, and it'll be really exciting to see what they find.
Can I just ask also one other one? Sorry, with the cloud that you had of people's thoughts of what the next 200 years was going to be about, did you have a word yourself that was up there?
Oh, that's a good question. Well, so I'm a radio astronomer, so I'm really looking forward to seeing what we get from the next generation of radio telescopes. And there are, I think one of the fun things that we have with radio telescopes at the moment is we're already getting that short survey capability. So we're able to actually look at the sky. There's a telescope in the Netherlands called LOFAR, which is a low frequency telescope. And they have a part of the system called the transient buffer boards, which sounds dreadfully boring. But what they do is they take 3 seconds of data and they analyze it in very, very fine detail to see if there's anything exciting, any transient signals in there that are really, really short. And they're finding some really interesting stuff in their data. And again, that's not a capability that we've had before. So I'm really looking forward to what happens next in that sort of transient space. I came to astronomy, I started out studying supernovae and things, so looking at the transients that last for a few months, but the really short-term stuff that we're seeing now, that we just, the energies involved are phenomenal. We really don't know the physical mechanisms for what on earth could be causing some of those transient signals that we're seeing. So I'm really looking forward to seeing what happens there next. So transients, that's where my excitement is, I think.
That'd be really good. Maybe we could have a talk on that in the future at some point.
It's on my list of talks to write when I get the time.
Thank you.
Any other questions? What other questions we got? I was going to ask one actually. I'm an old chap now, but I actually went around universities trying to decide whether to do aeronautical engineering or do astronomy back in the early 90s. And there were no women in the departments of any of the universities I went round there. And I decided to do aeronautical engineering because I felt it had a slight improvement in terms of diversity, etc. But how do you think we're doing in terms of, so that's 30-year window, things seem to have improved significantly, but how much further do you think we've got to go? So actually astrophysics as a career is welcoming to a complete diverse sort of workforce.
Yeah, I think it's a lot better than it was. When I was an undergraduate, there were, I think in my year, I went to university in, was it 1999? So we had about a fifth of my undergraduate cohort were women, which at the time actually wasn't great, but it's a lot better now. In terms of academic staff, certainly there's a lot of progress has been made at senior lecturer level, not so much at professor level, not so much at senior management level, but we are getting there. It takes time for it to filter through the system, and it does take, some people to shout and make a lot of noise and to be the first person in those cases, and other people to then follow on behind, but we're getting there. In terms of other sorts of diversity, I think we've got further to go, to be honest. In my department, there is, in terms of academic staff, there is no one who is not white. And that is a problem. And again, you look at the undergraduate population and it's predominantly, it is still predominantly male in most departments, and it is vast majority of them are white, which is an issue. That's one of the reasons why I do the things with the guys. So again, I'm really happy to see you guys doing lots of youth groups and so on, because if you can show kids that they can be anything they want to be, then they might actually go forward and have a career path that they might not have considered before. So one of the reasons I love talking to the girl guys is saying, look, I was you 20, 30 years ago, and I was interested in astronomy, and now I get to do it for a living, and you know what, it's great fun. So if you want to do it, there's nothing stopping you, go for it. And I think, yeah, having the opportunity to speak to someone who's doing that job is really powerful. So we need more ambassadors who are of diverse backgrounds to make that work. But again, that becomes a problem when you've got fewer of those people doing those jobs in the first place, because you end up with them doing all the work. So there's swings and roundabouts.
Okay, so we'll give it a few more years there.
Yeah.
Okay.
It is interesting because I work at the University of Bath, and it's something that we're trying to address there, because I've just volunteered to help out with Women in Electronics Day that's taking place. So they are trying to do more and more events like that to try and get women on board and excited about different bits of astronomy or electronics or engineering. And it's really important, like you say, to do that.
Yeah, that's fantastic. I think that kind of thing, if you can, I see this with the brownies all the time. If you go into a school and you do a talk about this sort of thing, a lot of the time the girls will sort of sit there and go, I'm not going to ask a question. But if you get a group of brownies, you can't shut them up. There's something about that in different environment where you're giving them permission to ask questions, and there's nobody there sort of staring at them, judging them. Outside of the school classroom, if you can break that, if you can break the dam, you can't stop them asking questions. And once you get past that stage, then you open up a whole world to them.
Definitely.
So Megan, if I was to give you a time machine, would you just whiz it straight on 200 years? Or would you actually sort of, if you've only got one trip, you can go there and go back, would you go 50 years? Let's just go find it all in 200 years. What would you do?
I don't know. I always said if I had a TARDIS, I would go and look at one of these events that I've been studying, because I could just answer all my questions without having to apply for telescope time. It would make it so much easier. Yeah, it would be good. I think I want to go further than 200 years. I think 200 years was, because we've had 200 years of the Royal Astronomical Society, so looking another 200 years was the point of the talk. But I think, yeah, I'd want to look a bit further in the future than that. And hopefully we've solved climate change, and hopefully the human race hasn't, blown itself up with nuclear weapons, and we understand the universe a whole lot better. So I think I'd maybe go 1,000 years or something and see what things are like.
Mm-hmm.
How far would you go, Prim?
Yeah, I think I'd agree, about 1,000 years, and hope there's something to see.
I was going to whiz forward 1 billion. I want to see Andromeda.
Well, yes, there is that. Yes. Well, so my previous talk, When Galaxies Collide, yeah, it does get as far as Andromeda, and in a few billion years, when it's that much closer and looking spectacular in the sky, would be really impressive sight.
I wish I was confident the human race would still be here at that point.
Well, yeah.
Do you have much hope for the SKA in terms of the problem of Starlink and satellites? Because the promises that Starlink made about visually sort of obscuring their satellites, it was great. They put in the visor sats, but they've just removed the visor sats in the latest generation because of the laser interconnectivity between them. So they've suddenly raised up in a magnitude in the last 2 or 3 launches. So they seem to have just listened and just gone and done their own thing.
Yeah, it's difficult because you're arguing with someone who's got to worry about their bottom line and their costs. They did experiment with coating one of the satellites as well to try and make it less reflective. The problem with that was it made it worse in the infrared because it absorbed more heat. So actually it got too hot, but also it was more of a problem for infrared telescopes. So it's difficult. I should say that both Starlink and some of the other companies as well, so OneWeb, they are willing to discuss with the astronomical community. So there are forums where these discussions are going on. So, there are a lot of astronomers who are doing the observational work to say, okay, this is the effect that it's having. There are others who are doing the detailed simulations and going, okay, this is the effect it's going to have on our surveys and on our instruments and on the planned telescopes, and this is a problem. This is essentially how much it's going to cost us in terms of wasted resources if we build this telescope and then we can't see anything. And given that it's public money, that's a serious concern. So because of that, of course, government are getting involved as well. So there is a select committee that is looking at the problem. There's one of the I think it's the science select committee is actually doing an investigation into this, and we are participating in that as a community, and the Royal Astronomical Society are as well. it is a problem, but the only way really this kind of thing is going to get solved. So we had a conference a little while ago, and there was a lawyer there who specializes in the law of space, essentially. Must be a fun job as lawyers go. And their point of view was, look, the only way astronomers as a group are going to really solve this problem is if they all individually complain to their local political representatives in whatever part of the world they are. If you get enough of your local representatives to care, then you might change the opinion of your national government. And if you get enough national governments to care, then the UN can do something. But that is the only way to seriously change what's happening, unless there's a massive collision, and then, you know, that might also force the UN's hand, but that would be a catastrophic scenario in so many ways. So if you care about it, the thing is, write to your local MP, try and organise a campaign, get your local MP on board, because that's the only way we're going to actually affect things seriously in the long run.
But practically, things like in terms of the SKA, as far as I understood, one of the biggest things was to get the compute together to actually just analyse the results raw. But now actually having to remove those additional signals, does that mean we're going to need bigger compute?
Yeah, so there are various, I mean, it's a problem for existing telescopes as well, right? So in the UK, we have eMerlin, which is run from Jodrell Bank Observatory, where I did my PhD. Series of radio telescopes that go, you can actually see one of them if you're on the train going down to Bristol. You pass one of the antennas on the right-hand side of the railway, a place called Defford. And they go all the way out to Cambridge. So it's 217-kilometre diameter radio telescope. And it's already being impacted by constellations. As I mentioned earlier, iridium has been a problem in the radio for years anyway. And the current methods of dealing with it are basically to get the data from the telescopes, run it through the correlator, the computer that does the initial processing, and then look at your data, figure out where the interference is, and just delete the bits you don't like the look of. You have to do that because if you leave it in, you can't image the sky. So it's a really significant problem even today, and it has been for 20, 30 years. It's getting significantly worse. Aside from getting rid of the data in post-processing like that, by humans doing it, which is a really slow way of doing it, there are people looking at whether we can do it with machine learning techniques. So do it in an automated way. And I've got a PhD student who's actually working on this right now. So again, in post-processing, looking at the data and saying, okay, can we train a computer to recognize what's interference and get rid of it? And that saves us an awful lot of time and means we can get to do the science faster. But again, it's diminishing returns. At the moment, we're losing significant chunks to RFI, the interference. The more of the band that we lose to this interference, the harder it gets to image the sky, because the more data you're losing, the less sensitive you get. So it is increasingly becoming harder and harder to do those deep surveys in the radio from anywhere on the Earth's surface, and the SK will be no different. One of the things that is being looked at for the SKA is actually whether it's possible to get rid of this interference at the telescope front end. So before the data goes to the correlator for processing. That's a much more efficient way of doing it, but technically it's much more challenging. It's hard to do it by retrofitting a telescope because you need, it's quite an expensive process, but if you can design it in from the beginning, much more sensible. So there are people looking at it. I hope they can make it work, because that would be a much better way of doing it. It won't solve the problem. You'll still have chunks of data missing, but hopefully it will go some way towards solving the problem, at least from a computational point of view.
Other questions? Any other questions that people have? What do they think the next 200 years holds?
Hopefully life, finding life, that's in mind somewhere.
Optimism as usual. Okay, well, we've just coming up to 9 o'clock, so I'd like to thank Dr. Megan Argo for popping along tonight. It's great that you're able to do this, and you've given us an insight. We won't come knocking on your door if you turn out to be wrong, and we have another COVID and things just. One of your predictions comes sooner. Hopefully it's not the Kessler syndrome in the next 2 years.
I hope so too.
Yeah. But thank you very much for your time, and keep all your good work going on, and we'll perhaps take you up on Prim's suggestion of another talk in the coming years. Thank you very much.
Yeah, I'll be happy to visit again. It's been a pleasure to see you all, and yeah, thank you very much for the invitation. And likewise, you guys keep up the excellent outreach that you're doing. It's very impressive.
We'll keep trying. Thank you, everyone. I'll say good night, and we'll see you back in September. Thanks, everyone.
Bye.
Bye-bye.